Tonight on BBC One, if anyone has first word of Earth being invaded, it's Patrick Moore.
Good evening. The VLT, or Very Large Telescope, is now being assembled in the Atacama Desert of northern Chile. In fact, it will consist of 4 telescopes working together, each with an 8-meter mirror, and the first of these mirrors has now arrived on the mountain and is in the telescope tube being tested, and that augurs well for the future. Meanwhile, the larger telescopes now in operation are the Keck's on Mauna Kea in Hawaii, and they've been used to discover the most remote object ever seen by mankind, a galaxy more than 12,000 million light years away, working now into the very early days of the universe. And much nearer home, the SOHO satellite is sending back data about tornadoes on the sun, whipping along at 300,000 miles per hour. Truly, the sun is a violent place. And now, on to our main theme. 100 years ago, photography took over from the human eye for most branches of astronomy. Now, photography is itself being superseded by electronic aids such as CCDs or charge coupled devices. Many amateurs now have them, and one is Martin Mobley, President of the British Astronomical Association. Martin, welcome to the Sky at Night. First of all, where is your observatory?
Thank you, Patrick. I actually have 2 observatories, one in Suffolk and one in Essex, and there are 3 main instruments. The largest is a 19-inch f4.5 Newtonian. There's also a 14-inch Cassegrain Newtonian and a 12-inch Schmidt-Cassegrain. This latter instrument is particularly suited to CCD imaging because it can be remote controlled from inside the house, so I can sit indoors in the warm and download images from outside, and many supernova patrollers are going this way with their instrumentation.
But you do use photography as well.
Yes, in fact 30 years ago I joined the BAA and I was inspired by the photographs of people like Horace Dall and Henry Hatfield and decided that I wanted to be an amateur astrophotographer, and we've got some of my photographs coming up here. A Hale-Bopp here taken with a normal camera lens. This was a superb object, most people saw this comet, and we have another image of mine, another picture taken with a long focal length instrument. But I actually preferred comet Hyakutake in March 96. This made a close flyby of the Earth. Unfortunately, in March 96, the whole of the UK was clouded out.
It was.
The weather was abysmal. However, Nick James, Glyn Marsh and myself fled to the clearer skies of Tenerife and obtained these dramatic photographs. And in fact, these pictures were taken with nothing more than an 85mm camera lens. Now, back in 1992, comet Swift-Tuttle made a comeback after 130 years, and I took this photograph at the time. It was 100 times fainter than the 2 other comets, but still made a nice target. Comet Levy in 1990, that's the large fuzzy ball at the top of the picture, made a close approach to the globular cluster M15 in Pegasus around about August 1990 when I took this shot through a gap in the clouds. And 2 objects you'll recognise straight away, the Andromeda Galaxy M31, which is a favourite target of mine, and the coat hanger asterism in Vulpecula. This looks remarkably like a coat hanger when it's shown this way up. And it's easily visible in binoculars. But these days I tend to concentrate more on images with CCDs.
CCD, charge coupled device, something very new, very modern and very exciting. Martin, some people won't know what it is. What exactly is a CCD and how does it work?
Well, I have one of my own CCD cameras here. This is one of Terry Platt's company's devices, the SX device. There's a glass window here. This end is screwed onto the telescope and light comes in through the window onto the sensitive CCD detector. And on the back of the camera we have some cooling fins here, and we have a 25-way parallel port connector which interfaces to the PC and via which you can download the images. There are smaller cameras available. This one, not much bigger than an eyepiece. Again, one of Terry's, has a CCD chip at one end and again a parallel port for computer interface at the other. And if we look at the chips in these cameras, they really are tiny. These are the actual heart of the device, the CCD detector itself. In fact, there's not much difference between a CCD camera for astronomy and, say, a camcorder or a digital camera. The main difference is that with a CCD camera for astronomy, we're taking exposures of minutes or tens of minutes. This means the camera has to be under software control from the computer. It also means that the CCD detector needs to be cooled. And in this diagram, a schematic of a CCD, we can see that light enters from the right-hand side, hits the CCD detector and its surrounding electronics are shown there, and the CCD is mounted on a cold finger from a Peltier cooler, which takes heat away from the chip and reduces the thermal noise. This noise is then radiated out of the back via the heatsink fins. A typical CCD chip contains something like 200,000 pixels, and in each pixel, photons are converted into electrical charge and then on to being a number in the computer. There are actually two types of CCD chip in use by amateurs. Firstly, the interline chips. Now in these devices, which are similar to camcorder chips, the image is downloaded in one go. It's downloaded via a shift register, as we see here, into the computer. However, part of the readout electronics obscure the imaging area, so they're not quite as sensitive as the alternate design, which is the frame transfer CCD. And in this type of device, we see that the image first is in the image zone, it's then transferred to the memory zone, and then again out to the computer via a shift register. And these devices are the most sensitive, they're also the most expensive.
Now, Martin, what exactly are the advantages of a CCD over what we call old-fashioned photography?
Well, the big advantage of a CCD camera is simply sensitivity. They are 10 to 20 times more sensitive than the most sensitive photographic film. The other advantage is that you can image process the image as it's a digital number. This is far easier than burning in and dodging and using horrible chemicals in the darkroom, which could take many evenings of work. Image processing is a powerful tool, especially in compensating for light pollution. Most amateurs who live near towns and cities are looking at galaxies and comets as if they were sitting on a sort of orange wall of light pollution. But with image processing, you can subtract most of this pollution and contrast stretch the remainder, which certainly increases the contrast of the image. If we look now at a diagram of how amateurs and professionals have got to fainter and fainter limiting magnitudes throughout the 20th century, we can see that Mount Palomar, for example, by the 1950s was getting down to about magnitude 23. Amateurs were doing not so badly, and when amateurs and professionals changed to using CCDs around about the 1980s, there was a 1 to 2 magnitude increase for both. But if we look now at the achievements on the right-hand side of the graph, on the bottom curve, Warren Offert in New Mexico, Cloudcroft, New Mexico, has a 24-inch Cassegrain, and he has been imaging to magnitude 23 some of the Kuiper Belt objects and the fainter moons of Uranus, which means he's imaging objects as faint as the Palomar 200-inch could get in the 1950s, which does show you the power that amateurs now have. If we look now at some images of mine, first we see a galaxy called NGC 7479 in Pegasus, lost here in the murk of light pollution, but a quick subtraction and contrast stretch brings the detail out. Now there's a technique called unsharp masking, which in effect is taking a blurred image of the original, subtracting it, and the result is a much enhanced picture, and it can be used for sharpening up the belts and zones of Jupiter or even deep sky images. And if we look now at this image of Jupiter, we can see an unsharp mask being applied. This is the original, rather blurred, and we apply the mask and it sharpens it up nicely. With the head of Comet Hale-Bopp, I've image processed this to bring out the bright inner coma detail, the concentric rings and hoods, and also the faint coma and the tail. And you couldn't cope with this range of brightnesses and detail with film. With the Galaxy M81 in Ursa Major, a 2-minute exposure with my 12-inch instrument brings out stars to magnitude 18.5, which would have taken 30 to 40 minutes with photographic film. An image of Saturn here I was particularly pleased of last year, but with unsharp masking the detail came out and the rings and the Cassini division were highly sharpened.
It's beauty.
And craters on the Moon, craters Snellius and Stevinus, benefit also from the unsharp mask technique. Now in 1994, in the Galaxy M51, the Whirlpool, you'll note that there is a small bulge to the bottom right hand of the galaxy. That is in fact a supernova, and quite a bright one. Unfortunately, because it's so close to the galaxy core, it would have been impossible to photograph with film. The film would have just overloaded the core and you couldn't pick the object out. But with image processing, you can easily pick supernovae like this out. And two comets, Comet de Vico in 1995 and Comet Utsunomiya in 1997, were moving quite rapidly against the background stars. In the old days of photographic film, you had to offset guide the telescope during the exposure. This was a problem and requires a great deal of effort to take a photograph of this kind. But with computers you can simply stack the images, take short exposures, and the computer allows for the comet's motion. It's a much easier way of doing it. Now, the man to beat as far as planetary imaging in this country is concerned is Terry Platt. We've mentioned him before, and he's a genius of planetary imaging. And we see here some of his images from his Berkshire back garden. This stunning image of Mars was taken by Terry. And then we have an image of Jupiter with one of the moons on the left-hand side and the shadow of the moon on the planet. And an absolutely exquisite image of Saturn in colour taken at the end of last year.
These are quite incredible pictures, you know, and after all there are obviously very many advantages over old-fashioned photography, but there must be disadvantages too. Be honest, Martin, what are they?
Well, there are a few disadvantages, that's true. We've already seen that these CCD devices have a very small imaging area. And this can be a problem because when you're trying to find objects in the sky with a detector this small, it's like looking for a needle in a haystack, unless you reduce the focal length of the telescope. Another problem is that the CCD chips themselves are pixelated, so if you enlarge the image to, say, the size of a magazine cover, it'll look very blocky and won't have the quality of photographic film. But another disadvantage, perhaps not originally foreseen, is that amateurs are making far more false alarm discoveries with CCDs. The reason for this is they have so much more power at their disposal and they can go fainter. And one of the worst cases of this is when amateurs image galaxies close to the ecliptic plane. Now, in the ecliptic there are loads of asteroids,
yes.
and with this sort of technology you can pick up asteroids that are very faint. Of course, amateurs photograph the galaxies, or image the galaxies rather, pick up the asteroids and think they've made a supernova discovery. Now, fortunately, in this country we have an excellent filter in this regard in the form of Guy Hurst. Guy's the UK Nova Supernova coordinator. He's also editor of the Astronomer magazine, and he has a team of checkers, including myself, who weed out the false alarm discoveries so that only the real discoveries get through to the professional astronomers.
Obviously, you need some electronic equipment. What about the cost?
Well, for a camera like this tiny MX5 unit, which we've already seen, the cost is only £500, which is relatively inexpensive. Some of the frame transfer cameras, particularly after importing from the USA, can cost about £2,000 to £3,000. You also need a home computer, of course, but many amateurs have them anyway, and you also need software. Many amateurs prefer to use Schmidt-Cassegraians, and we'll see in a minute that
yes.
the supernova patrollers all use them. This is because they can be remote controlled from indoors, so that you can guide, focus and slew the telescope while you're sitting in an armchair, and it's a lot more comfortable indoors than outdoors in the cold and damp. Now, at Conda Brow Observatory in Lancaster, Dennis Basinski has constructed a short focus 13-inch telescope. It's f3.5, and this is with the help of Glenn Marsh and of Nick James, who designed the electronic control system. This is a superb instrument for use with CCDs.
How much background technical knowledge do you need before setting out?
Well, you don't really need much skill in electronics, but what you do need is some familiarity with computer hardware and software problems. I have used image processing software that's been very frustrating, and after an hour or two I've literally lost the will to live.
I don't wonder.
Most people have had problems with computer software before now. Fortunately, in local astronomical societies and in the British Astronomical Association, there are always experts who can help you out with your problems. One piece of advice I would give: when you get a CCD camera and want to use it for the first time, try it indoors, not outdoors. You can attach with an adapter a 35mm wide-angle lens to a CCD camera relatively easily, and then image objects in a darkened room where the problems are far easier to sort out than in the damp and the cold and the dark outside.
Now, we've been talking about amateur results for CCDs. Can we have a general selection? Show us some.
Well, the results have been astounding. There's been an explosion of asteroid and supernova discoveries since CCDs were introduced. In fact, in the first 4 months of this year, we've had no fewer than 4 UK supernova discoveries. And we now have 4 UK supernova discoverers. And they are Mark Armstrong, shown here, who has 4 supernova discoveries, and Stephen Laurie, Tom Bowles, and Ron Arbour. And they have 1 each. If we now have a look at their discoveries, Here is an image by Mark Armstrong of the galaxy NGC 6627, taken in March. This was his second supernova discovery and his first this year. Then Ron Arbour followed up swiftly with a supernova in a UGC 3683 on April the 6th, but Mark then discovered another only a week later in NGC 3982 on April the 13th. If we go back to last year, Tom Bowles discovered a supernova in NGC 3451 in October, and earlier on in April, Stephen Laurie discovered a very nice supernova in NGC 3147, and this superb image of it was taken by another amateur, David Strange. In fact, only in the last few days we've had yet another discovery by Mark Armstrong, his fourth supernova discovery from the UK, this time in the galaxy NGC 6945. So Mark is doing very well indeed in this competitive field.
He is indeed.
Now, if we look at a list of supernovae discovered in 1997, and we scan down this list, in purple we have marked the amateurs. So we see Aoki in Japan with 5, Schwartz with 3 in the USA, and Bowles and Laurie with 1 each in the UK. In fact, there were 16 amateur supernova discoveries in 1997 and 147 professional discoveries. So amateurs are really encroaching into professional field, and their supernovae are the brightest, so therefore the most important as far as spectra are concerned. But if we move on to asteroids, we're in an even more astounding area. Now, Brian Manning in 1989 discovered the first asteroid to be found in the UK for 80 years. He now has 10 numbered asteroids to his credit, and a numbered asteroid is one with a good orbit. That equals John Hind's 19th century record of 10 asteroids discovered from the UK. Now, in the mid-1980s, we can see from this graph that around about 1985, the number of numbered asteroids with good orbits was standing at about 3,000. But following the use of CCDs by amateurs, that number has shot up to 9,000 today. But they're only the numbered discoveries. There are also provisional designation asteroids which have provisional orbits, and if we add the provisional ones to the numbered ones, we get the total number of asteroids known. That figure, remarkably, has now reached 39,000, so they truly are the vermin of the skies, as they were once called. Now, in the UK, Stephen Laurie has a total of 65 asteroid discoveries, one of which is numbered with a good orbit. We've already mentioned Brian Manning. He has 28, and 10 of them are numbered. In Japan, Takeo Kobayashi has an incredible 107 numbered asteroids and 1,782 total discoveries, begging the question, does he ever sleep?
I rather doubt it. What do you think comes next, Martin?
Well, all amateurs and professionals would like to see bigger CCDs for less money. Whether that will come, we just don't know. Adaptive optics, where a second CCD monitors the turbulence in the Earth's atmosphere and corrects for the Earth's shifting atmosphere by moving the optics 100 times a second, that technology is available off the shelf for amateurs. What really interests me, though, is that software is now becoming so good that we could see the day in a few years where an amateur puts his telescope outdoors, goes to bed, and the telescope makes the discoveries. In which case, are we going to credit the discovery to the amateur who owns the telescope or the person who wrote the software? In Arizona, the Spacewatch telescope has already discovered many comets automatically, but many more are discovered by people checking the images. The absolutely perfect automatic checking system is a bit like nuclear fusion, always supposed to be 5 to 10 years away.
Well, it may not be that. Certainly, astronomy is a fast-moving science. Martin, thank you very much. If you want the latest astronomical information, then dial up our Sky at Night information line, 0891 88830. And when I come back next month, I'm going to be joined by Dr. John Mason, and we're going to talk about planets of other suns. So until then, good night.